Section 7.5, higher coordination numbers, 7, 8, and 9. It is uncommon to find a coordination number of 7 or 8 or 9 in a transition metal complex. If you find such a high coordination number, usually the transition metal ion is large. It's a 4D or 5D transition metal. And the ligands are small. The ligands do not repel each other significantly. The ligands do not have too many lone pair electrons. The ligands do not form double bonds with the transition metal. What about the structure of the 7 coordinate transition metal complexes? This is a D5H point group, pentagonal bipyramidal structure, and this structure separates the ligands better than these two other structures. Over here you have a octahedron first, and then you put the 7th ligand on top of this triangular surface. So now you have 7 ligands bonded to the metal. But again, the repulsion between these two ligands, and these two ligands are more significant than between any other two ligands. Over here, we start from a trigonal prism structure, 3 on top, 3 on the bottom, and then we cap this trigonal prism with one more ligand. You can put it here, but also you can put it here. But if you put it here, there's going to be a stronger repulsion between this ligand and this 3 ligands. So if you put it here, that helps reduce the repulsion. Coordination number 8. So we can easily make a cube and then put the 8 ligands on the 8 corners. This is also OH point group, and this is the best way to separate these 8 ligands. And over here, this is example. We have 8 cyanidal ligands. They are pretty small, and this carbon has only 1 lone pair electrons over here. So this bond is formed from this lone pair electrons on this carbon. And then this carbon does not have any other lone pair electrons, and therefore the repulsion between these two cyanidal ligands is small. So that's why this transition metal center, this molybdenum, can form 8 bonds with this 8 ligands. When you try to name this compound, you look at this 8 and you translate this to octa, OCTA, octa. This is cyanidal. And then this is molybdenum, but you need to replace the ending UM with ATE because of this negative charges on the transition metal complex. Now coordination number 9. This is rhenium. So this is rhenium. Rhenium is forming 9 bonds with 9 hydrido. So H minus is hydride in general chemistry, but now it's called hydrido in transition metal chemistry. How do you name this? Nona, hydrido. And then over here, although this is rhenium, you need to replace the ending IUM with ATE. So it's going to be renate. Nona, hydrido, renate. The oxidation number of this transition metal center is +7. This is because after you assign the bonding electrons to the 9 ligands, each hydrogen is actually H minus. So you have 9 minus from this 9 hydrogen minus. So this transition metal center must bear a positive 7 charges. It's also possible to observe a coordination number of 10, 11, or 12. It's rare. It may be found in F block transition metal complexes. So here's one example. This Ce is cerium. It belongs to the lanthanide series, and it can form 12 bonds, 2 with each nitrato ligand. So this is nitrate in general chemistry. It's called nitrato in transition metal chemistry as a ligand. And over here, you can immediately calculate the oxidation number on the transition metal center, because each nitrate bears -1 charge, so this cerium bears +4 charges. The name of this is hexanitratocerate, because again you need to replace the ending IUM in cerium with ATE, because this transition metal complex bears negative charges.